Okay, all right. So here's what we were talking about last time. We were talking about the fundamental theorem of line integrals. Here it is, fundamental theorem of line integrals. And so I'm not going to repeat that whole discussion, but I do want to remind you of a couple of key points. Right? I mean, keep in mind what we're doing here is we're developing some ideas by ripping off patterns and relationships that we notice in previous contexts and trying to kind of let's do the same thing over here, see if it works. So we're finding patterns and then trying to apply those patterns elsewhere in other contexts. So this theorem, great though it is, right? If you want to compute a vector line integral, cool. Here's a formula that'll do it as long as your integrand is a gradient. But here's the key ideas that led to it. We started with the right side of the equation. And notice that this quantity, I'm going to call it change. You know, how much does the function change between A and B? This quantity change accumulates over the interior of the interval. Right? So that's a really interesting feature for an expression to have. Given a region, and suppose you break up that region, and I'm just going to recopy it kind of over here just to get it out of the way. If you break up that region into little pieces, right? There are certain quantities that we can associate to, let's say, an interval or a curve or what have you, that have this feature of accumulation. Mass, for example, the total mass on the whole is the sum of the masses of the individual pieces. Other things, ant population, etc. There's lots of different quantities, mostly that we think of as being kind of physical quantities, that have this feature of accumulation. What we're observing here is that change has this same feature of accumulation. The overall change, total change on a given interval or curve is the summation of all the little changes that happen on the individual pieces. Right? And change is not what we think of as a physical quantity. Right? So that's a little weird. Normally we think of this feature of accumulation as, look, stuff accumulates because it's stuff. Right? Mass accumulates because if you take a chunk of mass and you kind of cut it in half or whatever, you didn't destroy the mass. The mass is still there. That's kind of why mass accumulates. It seems to be a feature of something physical. Here we're seeing it as a feature of something algebraic. And that's weird. That should be an eyebrow raiser. That says that this quantity of change is going to have some unexpected features. So the fact that it accumulates, that's the first thing I want to draw your attention to. The other thing I want to draw your attention to is the relationship between the domain and its boundary that's connected in this result. In this theorem, if we have a curve, right, this quantity here, the right-hand side, is computed by looking only at the boundary. Right, you might say it's computed on the boundary. The other side of the equation, let's see, I'll use blue. The other side of the equation here, this vector line integral, that is computed over the curve itself. Right? So these two computations, and I think also one of the things that makes the fundamental theorem of line integrals, again, whoa, weird, how could that be? Is that we're talking about equating two things that are computed in completely different places. Right? The left side of the equation is computed on the curve. The right side of the equation is not. It's computed just by looking at the endpoints. Okay. So this aspect, the fact that this theorem says that there's something that's computed on the interior, but you could alternatively compute it just by looking at the boundary. This gives a relationship between an interior and a boundary, and as such, I like to call this theorem, and there's a bunch that will follow. I call them boundary theorems, and you'll see that right here. All right, so here's the fundamental theorem of line integrals fitted into our diagram, and you can see I've got it labeled as a boundary theorem. Okay. By the way, sometimes, because of the accumulation feature, I'll call these accumulation theorems. And I think that fits and makes a lot of sense, too. Okay. All right, so we're going to now proceed along to the next one of these theorems. A lot of details we talked about last time. We're going to talk about something called Green's theorem. And it's going to be morally kind of the same idea, just applied in a different context. Now, let me take a moment before I go on we've already kind of done that, right? We started with the fundamental theorem of calculus, change accumulates, algebraic games, and then there's the theorem, right? And then we talked about a new context, because instead of having a one-dimensional domain sitting inside of R1, talked about a one-dimensional domain sitting inside of R2. Okay, so we did go up a dimension, kind of, sort of in a way, but let's confess, it was still a one-dimensional domain. A curve, it's kind of like an interval, it's just bent, right? So, in a way, it was not that different, right? What we're going to do here with Green's theorem is way different. We're not going to talk about a one-dimensional thing and its boundary points. We're going to talk about a two-dimensional thing and its boundary curve. Two-dimensional thing with a one-dimensional boundary instead of a one-dimensional thing with a zero-dimensional boundary. So this is, very different context to apply, right? Now, this makes it hard to sort of extend the analogy. How do you see the analogy? Well, the diagram is going to do that for us, right? So here we've got this diagram, where we have all of our ideas organized, our different kinds of domains and the different kinds of evaluations that we do on them. And we argued through doing the fundamental theorem of line integrals. Let me go back to where that diagram is. Yeah, here we go. We argued through that, look, on this, you see it on the diagram, if you have a curve and you look at its boundary and then you evaluate like so, can you view this as being that kind of an evaluation? And if so, what is the corresponding integrand? Right? So now we're going to take this pattern on the diagram, and the way I'm going to extend the analogy up a dimension is I'm just going to do that. Right? I'm literally just going to shift everything over to the right. The diagram will then tell us what extending the pattern ought to be. So again, this is another wonderful feature of this diagram is the being organized with how we store ideas helps us see patterns between the ideas. Okay. All right. So yeah, here we go. Same game. Now we're going to find ourselves here. By the way, in R2. We'll talk about R3 a little bit later. But we have a domain, and we're going to look at its boundary, and we're going to evaluate to get some expression, and then we're going to ask, can I think of that as a double integral? And if so, what is the corresponding integrand? Now, that's the same exact pattern that we just talked through. One dimension to the left, right? But we're going to try to do this now for this raised dimensional context. Okay. All right. Well, the first thing that we did back here with the fundamental theorem of line integrals was made the observation that boundaries accumulate. Right? That if you look at the boundary of the whole curve, right? That's the same as the sum of the boundaries of the individual pieces that you chop it up into. And that was that whole sort of cancellation, you look at the two different pieces of curve, and this endpoint, well, it's sort of the ending endpoint of this subinterval, but it's the starting endpoint of the next, subcurve, and so it shows up as the boundary positively once and negatively once, and it cancels. That was that whole conversation. Okay, so does something like that hold for this very different situation? Instead of having a curve that I'm chopping up into pieces, what if I take this region, this two-dimensional region, what if I chop it up into little pieces? Do the boundaries accumulate? Is it true that if I look at the boundaries of each individual piece, if I look at that boundary, and then, don't forget this piece over here has a boundary. If I look at all these little boundaries, and if I add up all those little boundaries, do I get the boundary of the whole? That's going to be our first question to consider. So, all right, I'm going to start with what I'm going to call a relatively easy example. Let's look at a real simple piece, a little rectangle that we chop up into two smaller rectangles, just two, right? Just to kind of get our feet wet in this question, to sort of relate to the dimensional, the difference in dimensional context here. So we've got this whole thing here. All right. I'm going to chop it up into two pieces. We're going to chop it up into that piece and that piece. Now let's write down what are the boundaries of these individual pieces and what is the boundary of the whole, and then let's ask, do they add up the way they're supposed to? Okay. Well, now you'll notice the boundary pieces that we're talking about, there's a bunch of edges here. So I'm going to have to give names to these 7 edges just so I can talk about them. Now, I'm going to label these edges. It doesn't really matter how I label them. They're just edges, right? How they show up as part of the boundary of D1 and how they show up as part of the boundary of D2, that matters. That we have to be careful with. That we have to do right. Okay, but how I just label them in the first place, whatever. This piece here, I'm going to call that C1. It doesn't matter if I call it C1 or Q1 or whatever, and it could be anything it wants. And also, it doesn't matter how I orient it. I'm just thinking of this as an edge. I'm not currently thinking of this as being part of the boundary of D1. It's just an edge that I have to give a label to. So for kind of laziness purposes, I'm going to orient it that way. Right? So when I say C1, I mean that edge oriented in that direction arbitrarily. Okay. Likewise for all these other edges, and you can see I have little indications on each one of them, which way I'm orienting them. Again, totally arbitrary, doesn't matter. Okay, now let's talk about the boundaries. Let's look at this first piece here. I ask, what is the boundary of D1? Well, here we go. The boundary of D1 is, we've got that plus this plus this plus that. Notice the orientation does matter here. I'm following the rule. I'm going around in such a way that the region is on my left, counterclockwise. Right? And there's no interior pieces here. If you're going around the outside, it's counterclockwise. So I'm going around the correct direction. And how would I write these down? Well, I have here C1 going the direction that C1 goes. So I have positive C1. I have positive C2. I have positive C3. And I have positive C7. So the boundary of D1 is C1 plus C2 plus C3 plus C7. Yeah? Okay, now let's look at this piece over here. Let's talk about its boundary. Well, counterclockwise. Always going so that the region is on your left. So there's that boundary, and let's start adding up those pieces. What have we got here? Well, we've got C4 positive because it's going the same direction that C4 is going. C5 positive, C6 positive. But check this out. As part of the boundary of D2, I am going along that sort of middle edge, right? But I have to go the opposite of the direction that I've labeled as being the orientation of C7. So I'm going that fourth edge. That's negative C7. I'm going the wrong way. Very good. Okay. All right. So there's that. And now to test, do boundaries accumulate in this case? Is it true that the sum of the individual boundaries, does that add up to the boundary of the whole thing? Well, let's add them up. I'm going to add up this the blue boundary that I just wrote down plus this orange boundary that I just wrote down. Let's add these two things up. like the formula says, add those two things up. Now, you'll notice the C7s cancel. How about that, right? There's a plus and a minus, and it appears twice with opposite orientation, so it disappears in a puff of smoke. And all we're left with, kind of beautifully, is just these 6 edges, 1, 2, 3, 4, 5, 6, all positive. 1, 2, 3, 4, 5, 6, all positive, and sure enough, as desired, that is the boundary of the hole. Everybody on board? Did everybody see what happened there? Okay. So, this is geometrically very, very different from the one-dimensional, looking at intervals or curves. Again, they're not that different. They're the same things, just one's kind of bent around. The one-dimensional picture is very, very different from this. But not only does the result still hold, but the result still holds for, I'm going to say, kind of the same reason. Because whenever there's a shared piece of boundary, that shared piece of boundary appears twice in the summation, but with opposite orientations, and therefore cancels. It's exactly what happened when we were looking at the curve and you're looking at those interior shared boundary points. They appear twice, but with opposite orientations and cancel. So the analogy continues, right? So it's starting to look like boundaries accumulate. Now, admittedly, we've only showed this so far for a rectangle that you cut into a mere 2 pieces. What if I have a lumpy, weird, crazy shape like that? I'm going to simplify my picture before going on to that, just to make life a little bit simpler. Let me not put algebraic labels and do algebraic sort of work on this. Let me just represent the boundary of D1 looks like that. Forget about C1, C2, all that business. There's the boundary of D1. Here's the boundary of D2. And even without the labels, you can see right away that this shared edge appears in the summation twice, but with opposite orientations. Now, which one's plus, which one's minus? Who cares? I guess it depends on how you arbitrarily label that red edge as, which one is C7 up or is it down. But it doesn't matter how you label it. These are clearly showing up with opposite orientations. They're going to cancel. It's either plus and minus or minus and plus. Either way, it cancels, and you get the boundary of the hole, right? And you can apply this point of view to an arbitrary shape, right? However weird your region might be. Chop it up into a bazillion little pieces like this, and notice these, right, compared to these. That same thing's happening. This edge appears twice with opposite orientations and cancels. Right? Likewise, this edge appears twice but with that opposite orientations and cancels. This edge twice, opposite, cancels. Right? This edge twice, opposite, cancels. The same thing happens over and over again. This is just, in fact, intrinsic to the geometry of swirls, you might say, right? I mean, what is counterclockwise there and what is counterclockwise there mean two always exactly opposite things on this shared edge. So all of these interior pieces cancel, and then when you look at these sort of edge pieces of area, these interior ones cancel. All you're left with then is the ones that don't have anything to cancel with, and all that's left after the cancellation then is the boundary of the hole. So this always works. All right, so now we can proceed with our calculation, and here we go. Remember, what we were going to do is take a boundary of a solid two-dimensional thing. We're going to do a line integral of it, because the diagram tells us that line integrals are the object that is going to give us a nice result. So let's go ahead and let's play the winning game. Okay. Let's look at line integrals around the boundary of a two-dimensional region. Well, line integrals accumulate for the exact same reason that boundaries accumulate. If you're looking at a line integral around that boundary, and you're looking at a line integral around that boundary, then as part of doing those line integrals, you'll be doing line integrals on this edge twice, once in that direction, once in that direction. And those line integrals will cancel. Same thing, same argument. So, boundary line integrals accumulate. Just like, back when we were looking at the fundamental theorems, change accumulates. Same deal. Okay. Again, you can take a limit because you're taking a limit of a constant. This is always equal to the same thing, therefore it doesn't change, therefore it's constant, therefore its limit is itself. This kind of sort of looks like a double integral. We are adding up over the entire interior, after all. But to be a double integral, we need to have delta A on the side. So let's multiply and divide by delta A. Now, we have a 2-index Riemann sum, which is a double integral. Right? And okay, so we're almost done with deriving this new theorem. We are looking at a boundary calculation, boundary line integral on the one side. We've seen how it accumulates. We've rewritten that accumulation as a double integral. The only thing that remains is we've got to try to figure out what is this new integrand. When we were looking at previous theorems, we got lucky. We just recognized. We said, oh, hey, check it out. That's the gradient. How about that? Give me 2 seconds. We got lucky. It just happened to recognize it. That's the gradient. Or with the fundamental theorem of calculus, check it out. That's that derivative thing that we studied previously. So weird, right? We just lucky breaks. So no such luck here. This thing is not something that we recognize, but it is something that we can calculate. And there are details involved here. These are details that I think they take some time. They distract focus from what I think is really important here. Again, as y'all know, what I think is really important is to realize that this left side of the equation is an accumulating quantity. It accumulates over the interior, and that interior accumulation can be rewritten as a double integral. That's the point. That's the big idea that I want you to take away. The actual details of how to compute this thing, it's details. And here's the formula. It's this right here. It's dq dx minus dp dy. So we're just going to take that as given and not go into the details. So, yeah, you had a question.
Yeah. So I guess I'm confused about the application here. Is this like the amount of work that it takes?
Yeah, but right now we're just doing math. It's just math. So how you want to interpret this line integral? Yeah, you could view it as the amount of work that it takes to move around a boundary curve while opposing some, force. Okay, so maybe there's the wind is blowing in a kind of a circular way or something, and as you walk, in opposition to the wind, it's like you're walking into the wind the whole way around, right? Something like that. Or alternatively, keep in mind another interpretation of line integrals is if I were to think of this as representing a fluid flow, then this line integral represents how much that fluid is flowing along this curve. Right, along the curve as opposed to through the curve. And the twist here is that we're talking about how much the fluid flows along a curve that is going around. I guess it's going the other way. It's going around. And so you're kind of measuring how much the fluid is itself kind of making a loop. In a way, kind of, sort of.
So wouldn't that just be zero because you're going from your starting point to ending point?
Not at all. No, because literally, what if this is the flow of the fluid right here? Then as you go along, the fluid is flowing 100% along with the curve, the whole way along the curve. Right? Sometimes fluids go around like that. right? So yeah, it's not the same. Now, if this were representing gravity, right? Then yeah. Right? Then yeah, sure. Then f of b minus there'd be a fundamental theorem of line integrals problem, and it's a closed loop, and f of b minus f of a is actually f of a minus f of a, and yeah, sure. But not all vector fields are like gravity. Yeah. Yep. Okay. So we have ourselves a new theorem. Plug that into there. This turns into this, and amazingly, this integral computed on the boundary is equal to this integral that's computed over the interior. And so you'll notice already it's got kind of the same earmarks as the fundamental theorem of line integrals, which was an integral computed along the boundary, along the interior, that the curve itself is equal to an evaluation that's done just at the endpoints, just at its boundary. Okay. All right, so let's write this down as a theorem. Oh, by the way, so this little formula right here, very often in books it just gets written exactly like this: dq dx minus dp dy. And that's fine, that's what it is. But this expression comes up a lot, and there's a lot of syllables in dq dx minus dp dy. I kind of get tired of saying it. So I'm giving it a name. I'm naming this operator after the theorem that it connects to. This is called Green's theorem, and so I'm going to call this Green's operator, and I'm going to denote it as Green F. And I just mean the operator that's inside of Green's theorem. So that's a nice little shorthand. That's very convenient. So here's our new theorem. There's the theorem, and here's how it looks on the diagram. The pattern is identical. If you have a two-dimensional region in R2 and you look at, let me do it over here. If you have a two-dimensional region in R2 and you look at its boundary curve, and then if you look at a line integral of a vector field over that boundary curve, right, that does add up as a double integral over the original interior. It's a double integral over the original interior of this new thing called Green's operator. So there you go. Again, the pattern identical, same thing. Just shifted over as promised. Just shifted over one notch on the diagram. Okay. By the way, also notice a rewrite here. This is how we This is how we wrote the theorem originally, and notice I've rewritten that with my little shorthand, calling it Green's operator. So this is how I kind of prefer to write the theorem. It's a little bit more succinct, right? But most of the time you're going to see it with that. Okay. In fact, honestly, very often you're going to see this written as integral of p dx plus q dy. And so very often you will see the theorem written as that. Which, again, it's like, wow, that's a lot of notation that would summarize much more compactly like that. So anyway, you'll see it in all these different forms. Okay. All right, so let's do an example. Let's get our hands dirty. Let's see how to use this theorem. By the way, the first question you might ask is, what am I computing here? With the fundamental theorem of calculus, I had an integral to compute. Oh, here's a handy little formula for computing it. With the fundamental theorem of line integrals, same deal. Vector line integral. Wow. Handy little formula. Right? Here I've got two integrals. Which one am I computing with which other one? Right? And the answer is either way. So this is not so much a magic formula that just gives you answers. This is a I think still very surprising and very interesting theorem, which allows you to turn one question into a different question. right? So if you find yourself looking at a line integral, who knows? Maybe it's possible. You might find it easier to compute this double integral, maybe, and you've got that choice now, right? And likewise, if you find yourself looking at a double integral, you might conceivably find it interesting. I mean, you have the option now of maybe alternatively computing this line integral. Okay. All right. Most of the time, we use it this way. So we're going to, most of the time, be looking at line integrals that are hard and finding that this corresponding double integral is really nice. Okay. So, example. Let's compute a line integral. The vector field is given right there. There's a formula for it. The curve is this curve right here. It's the unit circle going counterclockwise. Okay, so I've got a vector field and I've got a curve. I want to compute this line integral. By the way, this could just as well be a chapter 5 problem, right? In chapter 5, we have formulas for this. You can parameterize that curve. You can plug that into the vector field. You can f dot x prime dt. It's a calc 1 integral and you can plug and chug. Totally. Again, let's take a moment to recognize how undesirable that would be. You trace out this unit circle, right? When you parameterize that, you're going to parameterize it probably with sines and cosines. Maybe square roots, but probably sines and cosines. Either way, parameterizing it's going to give you a little bit of algebraic ugliness. And all of that algebraic ugliness then is going to go into here. You're going to be taking arctan of trig and e to the power of trig, etc., which are then going to get multiplied by the derivatives of the trig, and your integral is going to be a great, big, nasty little monster. So let's call that plan B, plan C, right? That's not something we want to do. Okay. So here's the alternative. We're going to use Green's theorem. Let's remind ourselves what Green's theorem says. Green's theorem says, you got a line integral? Cool. We can rewrite it as a double integral. Don't go too fast. Do be careful about one thing. This does not say that you can compute any line integral whatsoever with no conditions. There is a very important condition here, and that is, you can see it right here in the statement. The curve has to be a boundary of something, right? This is not some formality like, you need differentiability or continuity, stuff that tends to always be the case in reasonable real-world scenarios that you can pretty much get away with ignoring most of the time. Right? That's not what we're talking about here. There are tons of curves that simply are not boundaries. Right? So, for example, that curve there, that's not a boundary of anything. And you cannot apply Green's theorem to that curve. Right? What's that the boundary of? Not even close to anything, right? And again, this is not just a formality. It's not that it has to be a boundary for sort of formal reasons. I need to know what it's a boundary of because that's the domain for my next integral. Right? So it is, this theorem is absolutely vacuous as it applies to this red curve here. It goes nowhere. Is everybody on board? Everybody see what I'm talking about? This is a big deal. Okay, so if we want to apply this theorem, we've got to look at our curve and make sure it's a boundary and that I know what it's the boundary of. So back to here. There's our curve. The unit circle going counterclockwise. Is that a boundary? Yep. It's a boundary of this. Boundary of that unit disk. Everybody on board? Everybody happy? Okay. Got to be really careful when you're applying Green's theorem. Oh my gosh, so often that I see students will And this is a dangerous little landmine. Lots of times students will take, an integral over a curve that's not a boundary of f dot dx, and they'll just completely uninterested in whether that's actually a boundary. They'll just say, oh, okay, double integral, and they'll kind of leave this blank, right? They'll just say double integral, and they'll write down Green's operator, dA, and then maybe they get lucky, and this might happen to be 0, right? Perhaps, and then they say, good, it's double integral of 0, that's 0, and they put a check mark and a happy face, and they turn the page, and never look back, right? And nothing that's written down on the page here is meaningfully useful, right? It's all garbage. If your curve is not a boundary, then there is no domain for this double integral. There is no double integral. The fact that this is 0 doesn't matter. There's no double integral in the first place. Making stuff up. Right? So, like I say, very dangerous landmine. Be careful. Don't step on this landmine. If you step on this landmine, nothing written down is true. I can't give any partial credit because it's not at all meaningful or valid. Super dangerous. Okay, you've been warned. I'm going to try to point that little landmine out elsewhere as we go along through the rest of the course for the next week here. But anyway, heads up. Okay, so back to this exercise. So we realize that our curve is a boundary, right? It's a boundary of the unit disk, right? It's a boundary of the unit disk. That means Green's theorem does apply. Green's theorem says I can rewrite that boundary line integral then as a double integral. No problem. The domain is my disk. The thing whose boundary is the curve. Oh, by the way, I have a terminology I'm trying to popularize. We'll hope this catches on. The thing whose boundary is the original curve, I like to call that the anti-boundary. I think that makes sense, right? It's kind of along the lines of antiderivative, along the lines of anti-gradient, the thing that undoes the... Anyway, for your consideration. So, double integral over the anti-boundary. And now we have transformed the question. Keep in mind our original question was to compute a line integral. Now we have rewritten that as a double integral, and fingers crossed, hopefully this is less ugly. Everybody see what's going on so far? Okay. Questions? All right, so now we do have to compute Green's operator. Fine. So I've got to take this vector field here and plug it in to see what Green's operator is. You got to compute it, right? I mean, it's dq dx minus dp dy. So the x partial of that. Anyway, the x partial of this, and then minus the y partial of that. And if you compute that all out, there it is, Green's operator. Lucky break, that's 0. That's 0 because these are partial derivative. Most of the ugliness just disappeared. I rigged up this example to be awesome, right? So, I mean, it's not always going to work out that awesome, but sometimes it will. And so notice then our Green's operator through this calculation becomes just 2. Nice, pretty little constant that factors right out. Right, and all we're left with then is the area of our unit disk, which of course is pi, and there you go, your answer is 2 pi. So, worked great. Yep.
Did you ever use that like which was going counterclockwise?
I'm sorry, say one more time.
Does it matter if the circle is going counterclockwise?
Yes, good catch. Let's talk about that. So, so notice the curve is going counterclockwise. And when I say that it's the boundary of the unit disk, that word is loaded. The word boundary means oriented boundary, right? And the oriented boundary also goes counterclockwise, right? So if it had been the other way, if this had been, let's change the question. If it had been clockwise, right, then our curve would have been that. And the boundary, though, the boundary would have been this. The boundary would have the opposite orientation, and I would just stick in a minus sign right there. Yeah, right, exactly. Great question. Everybody good with that? Okay. We're going to see that pop up at the next example also, by the way. Okay, so weird question here. It's another compute a line integral. The vector field is given right there, and my curve for this weird question is follows straight. It's in straight line segments that go between certain points, and I've drawn a picture of it. Here it is. So my curve does like that, and then goes down to there, and then goes up to there, and then goes back to the origin. So it's kind of a triangular figure eight, sort of, if you will, right? There's our curve, and let's compute that line integral over that curve. It's got 4 separate pieces. I would have to first parameterize that piece of the curve, work out that integral, and then I would, if I were taking a chapter 5 approach, then have to parameterize that, do a line integral, parameterize that, and do a line integral, then parameterize that, and I would have 4 separate line integrals. Again, let's call that plan B. Nobody wants it. It's ugly. It doesn't work. Okay, effort. Okay. Let's ask the question, can I use Green's theorem? Well, the sticky wicket, of course, is this has to be a boundary of something. Is this curve a boundary of something? Now, it's tempting to say, yeah, it's the boundary of these 2 triangles. Everybody see how that curve appears to be the boundary of those 2 triangles? Orientations are going to mess us up, though. So let's think it through. Notice I have the orientations written on here as to which way we're going along our given curve. The boundary of D1 is like that. And notice, positive orientations each time. So the boundary of D1 is those 3 sort of pieces of these pieces of curve. So cool. Looking good. What's the boundary of D2? Now again, forget about the curve. Forget about the orientations that were given on the curve. We got to think about what is the rule. We have a region D. Boundary goes which way? Boundaries go, I'm going to again sloppily, forgive me, say counterclockwise. And notice that has me going the wrong direction. All 3 pieces. I'm going the wrong way there, the wrong way there, and the wrong way there. Okay, so it is not boundary of D1 plus boundary of D2. It just isn't. So that's bad news. Right? But sometimes bad news is not that far off from good news. So it is true. It's true that these orientations are going the wrong way, but here's another way to say that. They're all going exactly the wrong way. Right? So in fact, one way I could write this is, let's think about negative D2. Right? Let's think about the boundary of here, let me write it like this. The boundary of negative D2. A negatively oriented 2-dimensional region, the boundary is just going to be the exact opposite of the positively oriented 2-dimensional region. So the boundary of negative D2 is going to be just go clockwise around each piece. That gives me exactly what I want, right? And so the boundary of negative D2 is the thing that I need. All right, so with that in mind, what we're talking about, the anti-boundary, it's not D1 plus D2, it's D1 minus D2. How we doing? Ready good? Sweet. Okay, so good deal. We have ourselves an anti-boundary, and so Green's theorem says that this curve, which is that boundary, Green's theorem allows me to rewrite the line integral as a double integral. And now I just have to compute a double integral over this domain D1 minus D2. Now remember, when you have domains, different sort of domains that you're all plugging into the same integral, you just compute those integrals separately. So I'm computing the integral on D1 minus the integral on D2. Okay, and now I've got a couple of separate integrals. By the way, you can compute Green's operator. Now this, again, is a little bit of algebra, but take this function, this vector field, plug it in, compute Green's operator, and it's 1. Easy calculation. Lucky break. And so I have a couple of areas. I'm subtracting 2 areas. These areas are clearly equal. So I'm subtracting this area from itself, and therefore my answer is 0. Isn't that nice? How are we doing? Is everybody okay? All right. Alrighty, moving along. Okay, so there are this example here. I'm going to let y'all read. This is a nice example about certain vector fields have a certain nice feature, and so these coordinate line integrals, these special coordinate line integrals, always 0. This is an easy application, and in fact I think this is an exercise. So I'm going to let y'all read through that application on your own. Okay, one other example I want to show you. Now this goes back to, let's go back to here we are. Here's our theorem. I made the observation already that most of the time we go that way. Most of the time we find ourselves interested in a line integral, and computing it as a double integral is the desirable move. We've seen 2 examples of that here now. Okay. Sometimes it goes the other way, and it's just as valid, right? An equal sign goes both ways. So I'm going to show you an instance where there's a double integral that we would like to compute, and it is actually easier to compute the corresponding line integral. It's a very specific application. It has to do with area. So suppose I want to compute an area. Here's an example. Here's a really hard area that I might want to compute. Right? This is some wacky polygon, right, sitting up in space. I've arranged it to where none of these angles are nice angles. These lengths are all square roots and stuff, right? So I've got a crazy, wacky region here to compute the area of. That's a hard problem. There's different ways you can think about it. But anyway, I'm going to call this and I think you'll believe me, hard problem. Right? Well, it turns out you can compute this area, aka this double integral, right, over this region. We're going to compute that double integral with a line integral, and using Green's theorem. Right? And it's a clever little move. I wish I thought of this. Somebody showed me this move. It's a slick move, right? So I didn't make this up, but I get to use it because somebody showed me and I understand. So now we're going to do the same thing here. I don't expect you to have dreamed this up yourself. This is a very slick move, right? But you get to benefit from, me passing this down here. And here's the idea. Let's think about that vector field. Let's compute Green's operator of that vector field. And it's dq dx minus dp dy, which is 1. Green's operator is 1. Isn't that nice? So that's a special vector field, 0, x, special vector field. It has this wonderful feature. Green's operator is 1. By the way, it's not unique. There's plenty of vector fields whose Green's operator is 1. Make up your own. Feel free, right? This would be my nomination for the easiest vector field that has this feature, but there are plenty of others. Okay. Alrighty, so Green's operator is 1, and that makes this result really easy to prove. The claim is that area is computed by this coordinate line integral around the boundary curve, and notice that coordinate line integral is a vector line integral of that vector field. We're doing a boundary, so we can apply Green's operator. Green's theorem. Green's operator was 1, and sure enough, I get area as I claimed. Right, lovely little convenient proof thanks to Green's theorem. All right. Now, so you say, Yeah, but now I still have to compute a line integral. Isn't that annoying? Look at all the pieces on which I have to compute a line integral. I've got 5 pieces now to compute a line integral. Here's another theorem that's super handy sometimes. Also easy to prove. Now this is an exercise. This is literally an exercise. You're going to do this as part of the homework. But prove for yourselves this integral, this special integral, integral x dy, on a line segment. That integral always has this nice, handy little result. It's just the average value of x times the change in y. So you can see that in how the arithmetic works out here. The average value of x, the average of the two x endpoints, times then the change in y, namely the height at the end of the line segment minus the height at the start of the line segment. So the way you're going to prove this is you're going to parameterize that curve that starts from the point x1 y1 and goes to the point x2 y2. Just write down a parameterization. That parameterization is a chapter 1 problem, right? You can kind of a plus tv parameterize that thing. Plug that parameterization straight into here and chug away, and out comes this answer, namely that answer. So it's a good exercise. Everybody should do it. Okay. But the application of this is fantastic. I need to compute, keep in mind, a line integral over this boundary that has 5 pieces, but each piece is a line segment on which I can use that formula. Right, so really all I have to do is, I'm adding up 5 line integrals, but that just means I'm adding up this formula 5 times as applied to, looking at the vertices of these 5 different edges. And you can crank out, there's a bunch of little arithmetic in here, but applying that to the polygon above gives you this arithmetic. And it's a little annoying, but it's 4-function arithmetic. It's pretty straightforward arithmetic. And there's your answer. It's 17/2. And I suggest that this beats the alternatives. Right? Think about this from a high school geometry point of view. How would you compute that area? Right? Nightmare. Not bad. Okay. So that's Green's theorem. Moving along. Guess what we're going to do next? We're going to apply the same ideas, just in a different context. Let me remind you I'll go back to the page. The ideas we just got through applying were in R2. Take a region, look at its boundary, do the evaluation. Ask, does that accumulate as a double integral over the original region? And if so, what is the new integrand? And the answer was, it's this thing called Green's operator, and that's so our new object in our diagram. Green's operator there. Okay. We're going to follow that same pattern in R3 now, 3 dimensions instead of 2, right? And it's the analogies are overwhelming. Y'all have hopefully started to notice the pattern, so I'm going to move a little bit more quickly through the pattern here. We're doing this 3-dimensional version of the theorem. We're going to start off. So here we are. We're going to in R3. We're going to take a solid, a 3-dimensional solid. We're going to look at its boundary. We're going to compute a flux. Diagram tells me so. I'm trusting the diagram. Right? Let's compute the flux over that boundary surface, right? We have a 3-dimensional solid. 3-dimensional solid, it's got a boundary surface. We're going to look at the flux through that boundary surface, and we're going to ask, because the diagram tells me so, can I view that as a triple integral? And if so, triple integral of what? I mean, now I don't know if any of this is going to work. Right? But golly, this pattern's worked 3 times now. It's worked fundamental theorem of calculus, fundamental theorem of line integrals, Green's theorem, all dimensionally different contexts, same exact pattern, it keeps working, we're optimistic. This seems like it's got potential. We do have to go through and check to make sure everything adds up. No pun intended. Okay, so first step, do boundaries accumulate? Now, reminder, we are looking at, in R3, we're looking at three-dimensional solids. Those are the things whose boundaries we're talking about. So three-dimensional solids have boundary surfaces. Do those boundary surfaces accumulate? That's what we want to ask. Whoops. Oh, come on, button. Here we go. So here's the first picture. I've got a great big solid thing here. Right, great big solid thing. And I'm going to chop that thing in half. Now I've got two pieces. I've got this piece over here, and I've got this piece over here. And I would like to ask the reasonable question. If I look at the boundary, now keep in mind this is a three-dimensional solid. The boundary of a three-dimensional solid is a surface. If I look at the boundary surface of that left half, if I look at the boundary surface of this right half, and if I add up those two boundaries, do I get the boundary of the whole thing? It's a matter of writing it all down. Now, again, look, we could give names to all of these faces and assign orientations and do all this algebraically, but I think it's much easier just to draw the picture of what these boundary faces look like, draw arrows indicating the orientations, and just look at the pictures. Right. So let's start with this left half. Right. That left half has a bunch of faces. There's this face there, oriented that way. Keep in mind there's rules for orientations of boundaries. Right. Orientations of boundaries always point away from the solid, outward. Yeah. Okay. All right. Then there's let's see here. There's this face oriented that way. And then there's this face oriented that way, et cetera, et cetera. The one that's going to matter is this one oriented that way. So that shared face is part of the boundary of D1, part of the boundary of the left side, oriented as part of that boundary, it's oriented to the right. Okay. Now, let's look at the other side. This solid, its boundary consists of, well, we've got that face oriented that way, and we've got this face oriented that way, et cetera, and among others, we've got this face, and as part of the boundary of D2, it is oriented that way, again, away from the solid. Yeah. Okay. So, this face here, that face, if we look at the boundary of D1 plus the boundary of D2, that face appears twice. Once as part of the boundary of D1, then separately as part of the boundary of D2. Notice that this face then appears twice with opposite orientations and cancels, just like every other one of these boundary contexts that we've looked at, right? The geometry is different. It's faces instead of edges or boundary points. The geometry is different. It's the orientations are normal vectors instead of, tangent vectors or pluses and minuses in the other contexts. But it remains that shared faces appear twice with opposite orientations and cancel. Now, this was two. This is a simple figure that I chopped up into a mere two pieces. What if it's more complicated? Well, look, the picture gets real hard to draw, right? So forgive me for having limitations on here, but let's imagine this great big lumpy solid, and I chop it up into a bunch of little, mostly cube-like little things like that. Well, that face right there is part of the boundary of this little cube oriented that way, right? But it's also part of the boundary of that cube oriented this way. And so that face appears twice with opposite orientations, and it cancels. And etc. All of the shared faces. Now, different little picture on each one of the shared faces, but every shared face cancels. Right? This shared face right here cancels. Same reasons. And all that's left after you cancel all those shared faces, the faces that are not canceled are the ones over here on the edge, namely the boundary of the actual original solid. So, like I say, the picture is harder to draw, but it's all the same ideas. And so, boundaries accumulate as sums of boundaries over the individual interior pieces. Everybody on board? Questions? Feel free. Geometrically hard. Okay. All right. Okay. So here we go with our pattern. We are going to look at a solid, take the boundary, talk about the flux. We want to ask, can that flux be thought of as a triple integral? In other words, does flux accumulate over the solid? Well, look, it's the same picture that we just drew. In the same way that the boundaries accumulate, the fluxes also accumulate. If you look at the flux, the boundary flux of some vector field through that boundary surface, among other things, you'll be looking at the flux through that face with that orientation. And you'll also, as part of the boundary of this, be looking at the flux through that same face with that orientation. And so when you're adding up all the boundary fluxes, the flux through that shared face will appear twice with opposite signs that cancel. Same deal. So the first step that I'm going to write down algebraically in looking at the boundary flux is to say that boundary flux accumulates. Now this is a kind of scary looking equation, right? Let's focus on just this one equation here. What I've got, though, is a quantity that I'm computing over the whole. Boundary flux is what I'm computing on my original solid, D. I've simply made the observation that the boundary flux on the solid is the summation of the boundary fluxes over the individual little pieces, and then add up over all the pieces. So this is just an algebraic way, a scary algebraic way, but it's just an algebraic way of writing down boundary fluxes accumulate, just like boundary faces accumulate. Cancellations. That's all this is really saying. Okay. So with that noted, we're just going to follow our previous pattern. This expression right here is always equal to the same thing. Therefore, it's independent of n. Slice up all you want. You're always going to get this same answer. So since this is a constant, you can take a limit. Doesn't change. This kind of looks like a triple integral in the sense that we're doing an accumulation over all the pieces of a solid. We've done a chop it up, add it up kind of sort of looking thing here. Anyway, we've got a summation over all the pieces. The problem, of course, is there's no dv over here. Right? So we will multiply and divide by dv. Got to be fair, right? Got to be legal. Now this really is. It looks a lot like a triple integral. And you can see right there, limit of a sum. We've got some thing here, and then times delta v. That's a triple integral. Sweeping some formalities under the rug that are not our concern in Math 212. I'm just going to write this as a triple integral. I do need to talk about this interior in the limit our integrand is going to become that. We again find ourselves faced with, we kind of want to celebrate here. We've got a boundary flux written as an interior triple integral. Seems good. The only thing is, I don't know what this integrand is. What is this integrand? Don't recognize it. Oh well. You can't always get lucky, right? We got lucky with the fundamental theorem of calculus. We got lucky with the fundamental theorem of line integrals. We didn't get so lucky with Green's theorem. We had to there had to be some work done on the side to compute out, how do I compute this thing? And likewise here, no particular luck. This has to be worked out on the side. It's details. On the exercises, I'm going to have you go through a sort of a special case, kind of a bare bones, simplified version so you can kind of get some idea of how that calculation would go, stripped down conveniently, right? But I want you to have some intuition there. But the point is it can be computed. And here it is. That thing is computed with this formula. And it's an easy little formula. It's computed straight out of the components of the vector field. Keep in mind we've got this vector field that we're talking about doing the flux of. Has components PQR. Just take partial derivatives of, easy partial derivatives. The x partial of the first component, the y partial of the second component, z partial of the third component. It's an easy little formula. Add them up. And that's how you compute this integrand. So that's our theorem. I'm going to take this formula here and stick it into there, and that's our theorem. Let's see, did I write that down? Yeah, here we go. So the theorem becomes this. All right. How are we doing? Is everybody okay? All right. Before I append the diagram, I'm going to do a notational thing. And remember, we were talking about Green's theorem. The thing that was on the inside, it was a bit of a mouthful, and so I gave it a name. For convenience. That's already been done here. This thing already has a name, so I don't have to make something up. This is called divergence. And so that formula right there, you can just write div f, and that's very convenient. A lot of books will write it like that. It just makes loads of sense, right? Who wants to actually say dp dx plus dq dy plus dr dz every single time? Right? It's nice to say divergence. Okay. There's another little notational thing that I want to talk about, and this is this takes a little bit of developing, but it's very, very cool. I really dig this, and it's also very, very common. You're gonna see this again in my past life as a physics second major. When I saw just a bazillion instances of divergence. It gets used a lot in physics, and it will get used a lot in engineering for those of you who are engineers. The notation I'm about to show you was even more common than this notation. Okay, so this is important. So, but we have to rewind real quick. I want to remind you we have this thing called the gradient vector, and there's our formula for we have a notation and a formula for gradient. Now, this may seem a little weird, but I'm going to kind of this seems strange. I'm going to think of the action of taking the various partial derivatives. I'm going to think of that as a separate thing called an operator that applies to the function f. What do you think? If you were to guess, what would I mean by applying this to that? You would guess this. Right? Okay. So I'm going to think then of this thing as being kind of a formula for what that symbol by itself is. Now, you've got to be careful with the terminology here. You cannot say that that is gradient. That's not gradient. That's gradient. I'm talking about just the operator by itself. So this gets called the del operator. Let me do this. Here we go. This is called the del operator. So you might say, if you want to talk about the gradient, you might say del f. By the way, I rewrote it down here. Okay, so del operator. So del f is another way of saying gradient of f. Okay. now, with this del operator, weird thing. By the way, let me also recognize that looks kind of nonsensical. I'm writing it like it's a vector. What direction does this vector point, right? That's not really a vector. I'm kind of fibbing when I'm going to write it like a vector as if it's a vector when it's obviously not a vector. So apologies. Again, this is, symbolic convenience, kind of like that formula for determinant way back when. It's a very common practice, and this can all be made okay, but it's forgive me in this context. So with our new little toy here, our del operator, let's look at our formula for divergence. Here it is, divergence from the previous page. And notice divergence, you can see that del operator right there in the formula. And in fact, you can see that it's almost like we're sort of doing a dot product with the vector field. I mean, sort of. I mean, again, not really, right? I mean, dot product, if you want to get all strict about it, we've defined dot product as a formula that applies to two actual vectors. So this is a stretch, but it's a pretty believable stretch, and it's super convenient. So look at how easy it is to write divergence with this understanding. Del dot F, a vector field. So this formula for this notation for divergence, del dot F, very common in physics. It's almost, I don't want to say, anyway, it's extremely common in physics. And I assume then also probably engineering. So for your consideration. So I'm going to use a lot in this course. I'm a big fan of this notation. So you'll notice that's how I've got my diagram appended here, or the operator, our newfound operator, divergence, and I've got that del dot notation right there for your convenience. I'm also putting the little div notation, reminder. And then here's the theorem, del dot to represent divergence. So our theorem, boundary flux is a triple integral of the divergence function derived on a previous page. And seeing that on the diagram, just to remind you that the diagram chase works again just like it did in the previous context. What we did here is we started with a three-dimensional region in R3, talked about its boundary. The diagram tells us, and we obey, check out, I should do that in green, check out the flux of some vector field through that boundary. Again, doing what we're told, right? We ask reasonably, hoping that the pattern continues, can this be thought of as a triple integral of something, and if so, what? And the answer was divergence. So the exact same pattern continues to hold. Gauss's divergence theorem, fundamental theorem of line integrals. In two dimensions, the same pattern gave us Green's theorem. Right, the pattern is very strong. Okay. All right. Let's see how we're doing. Okay. Okay. So again, question comes up: how do you use this? What do we actually compute with the divergence theorem? Neither one of these is handy dandy little formula that you can just plug in, boom, answer, right? Both of these are kind of hard things to compute. So do we tend to use this to compute, we're trying to compute a flux integral, hey, triple integral will compute that for you. Or is it that we're going to find ourselves interested in a lot of different triple integrals, and we're going to find it very convenient to compute them with flux integrals? You can go either way. It's true either way. Most of the time, we want to know a flux, and we find that it's easier to compute it with a triple integral. Most of the time, we use this theorem to the right. Okay. All right. The same landmine as with Green's theorem. Same landmine. Arguably even a more common landmine to step on. If you want to compute a flux, you cannot apply Green's the Gauss's theorem to just any flux. Note, and it says right here, flux through a boundary surface. It's got to be a boundary surface. This only applies to boundary fluxes. And then that allows you to use this formula. Again, not just a formality. There are plenty of surfaces, such as that piece of paper, an angled piece of paper, just a segment of a plane. That's not the boundary of anything. Right? So to call that a boundary and then just start writing down triple integrals is meaningless nonsense. Right? Absolutely meaningless nonsense. So, oh my gosh, be careful with this. So common. Students will find themselves looking at a flux and they'll have something here. Let's some surface, and let's suppose that it's not a boundary. So often, and it's heartbreaking every time I see this, students will say, okay, I'm just going to say triple integral of divergence because that's awesome. And maybe it turns out that that's actually 0, in which case there's this temptation to say, triple integral of 0, 0, boom, walk away. Nothing on the page here is correct. I can't give any partial credit for this because nothing is valid and true. Everything here is meaningless garbage. There is no triple integral. There's no domain. Therefore, there is no triple integral. The fact that this is a 0, so what? Right? The answer is wrong. The reasoning is wrong. So I beg you. I make this appeal every year, and I think I've cut down pretty substantially on students stepping on this landmine. But I have not completely exterminated this problem. Some students are still, I think, probably going to do this at some point, and I just, fair warning, I can't give any partial credit for this. Okay, so always check. So important. If you're going to use Gauss's theorem, check and make sure that your surface actually is a boundary of an actual three-dimensional solid domain. Okay, all right, we'll pick up here next time. See y'all later.